Crash Course Instrumentation, Episode 13, Source Behavior Under Load. Welcome back to Crash Course Instrumentation. Today we're getting into something every tech has seen, even if they didn't know how to name it. Why does voltage sag when I add a load? We're exploring source behavior under load and how real-world power supplies don't always behave like the ideal sources you see in textbooks. Let's get into it. Ideal versus real voltage sources. An ideal voltage source delivers constant voltage no matter what load you connect. But in the real world, that's not how it works. Every real voltage source, battery, power supply, or generator has internal resistance, sometimes called source impedance. This means as you draw more current, the output voltage drops. The more current you pull, the worse the sag. This is why a 9-volt battery that reads 9 volts on a multimeter might dip to 6 volts the moment you connect a motor. Even regulated power supplies have internal limitations. When pushed past their rated load, many supplies enter current limiting mode or shut down entirely to prevent damage. Visualizing internal resistance, you can model any real-world source as ideal voltage source plus internal resistance in series. It's like a resistor hiding inside your power supply. The voltage you get at the terminals depends on the load. No load? You get full voltage. Heavy load? Voltage drops across the internal resistance. Bonus. If you scope the voltage of a supply under pulsed load, like a solenoid or stepper motor, you'll often see a ripple or dip at each activation. That's internal resistance reacting to the load. This concept also helps explain brownouts, where supply voltage dips low enough to confuse digital systems without fully powering off. Why this matters in instrumentation. In real control systems, this concept helps you size wires and loads properly, avoid voltage drop over long runs, choose the right power supply for your devices, know when a power supply is failing before it shuts down. Understand why sensors might act flaky or PLCs reboot during startup. Example, if a 24-volt supply dips to 21 volts when the process starts up, that might trip your PLC or analog input. Even worse, it might cause intermittent behavior, which is harder to diagnose than a clean failure. Also, internal resistance increases over time, especially in batteries. That's one way to detect aging supplies. Real-world examples. A benchtop supply might be rated 24 volts at 3 amps, but as you get closer to 3 amps, you may notice the output drops a bit, unless it has good regulation. A weak car battery might still read 12.6 volts at rest, but crank the starter, and it sags to 9 volts. That internal resistance is telling you it's done. In 420 milliamp loops, too much loop resistance causes voltage to drop before the current can even reach the transmitter. That's why you calculate loop burden. Long cable runs in field wiring act like extra resistance, reducing voltage to field instruments. This is why voltage drop calculations matter even at 24 volts. For switching power supplies, transient loads can briefly overshoot or undershoot. This can trigger false inputs if filtering isn't used. Quick tech tip: want to estimate the internal resistance of a source? Here's a simple trick. 1. Measure the open circuit voltage, no load. 2. Apply a known load and measure voltage under load. 3. Use Ohm's law. Resistance ohms equals volts divided by amps. Ohms equals sols. Voltage open circuit minus voltage load divided by load amps. This helps when designing or troubleshooting tight tolerance circuits or analog signals. Also, when using backup batteries, always consider the internal resistance at cold temperatures. Resistance increases sharply in low ambient conditions. Wrap up: real-world sources have limits. Internal resistance equal voltage drop under load. Know it, measure it, and plan for it. Helps prevent nuisance trips, brownouts, and misreads. Thanks for watching Crash Course Instrumentation. Be sure to check out the Model PDF on Source and Load by Tony R. Cupalt for more open-source awesomeness. And don't forget to join our Facebook group. See you in episode 14, where we'll simplify circuits like pros using Thevenin and Norton equivalents.